Good morning, everybody. Well, just looking at the screen shows up on here. It's weird they didn't align the camera 90 degrees off. Because they've got this weird extra side stuff where you can't see the whole paper. I was looking like, well, I didn't worry, but here's what it is. I guess let's go with the projector. If I said I can just do all my papers sideways. I don't know if you can write this one. Just writing on a white piece of paper. Hey, maybe I'll give us, I'll open our relationship with papers and it's more to it. Okay, so last time we went through, we talked all about ripple carry actors. Right? We went through, we talked about how to test it. We introduced the idea of a test bench on it, and the idea to simplify the process. So that's really where your task is, right? To write that up, put in, figure out what particular sequence of bench you're going to do, and test that program. Do program it also to your folder, right? And then take a couple pictures, do the same things as you did on in the test bench, and just don't have a picture that you get them. It's easier than having me take through it. So when you're doing your testing, do the simulation, pick the test cases, say why the test cases, do those same test cases, and just take a picture with your phone or something, and you can include that picture inside your lab report. Upload the lab report and the system Verilog, and that work. Again, grad students individually and undergrads individually. At this point, we should then ask the question, right? Because if you notice, there's, I'm going to have you do two more different types of matters. I do another type of matter. You've got something that works. Just works. We say, oh, don't mess with it. Same thing, don't fix it.
Well, I'm bad about that. We unfortunately have multiple scenarios in which the now, this matter may work good here, may not work so well here. So we have to think, well, what's the scenario we want?
Yeah, and if you're going to make in that type of logic scheme, in one sense it is broken. Right? A ripple carry adder is broken. How can I justify that statement? It's true in a sense. You have to get the sense right. It worked. Anybody got an idea how it's broken? How do you think it would be a good idea for me to be the U.S. representative to the Olympics in the 100-meter dash? It's mid 50s. Try that. If I was, it's funny.
Broken in the sense that it's broken in the sense that it's slow.
It's slow. That's really the issue right there. That's why I didn't joke about me and the other guys. Right? In one thing, people take it right? But another thing which you don't want that representing a country. There's a lot of people who can do it. Well, what is the main goal? Your typical user wants the machine speed. Anybody like when people talk about their machine and they're talking about something that's not happy with their machine, they're happy because their machine is faster than your machine. Right? They can do a better job rendering their games, but they shoot you better. because that's what friends want to do in the game, to shoot each other and totally get into the face. Right? Because we call that fun. Okay? When people say we all know it, and that's all about having a faster machine. Well, think about this. If I've got a ripple carry adder, let's consider that complexity. And this is where we're going to talk a little bit about complexity. So we've got, our full adder here where we're going to break our numbers and it's going to look like this, right? I've got my bit 0 from X and Y and bit 1 from X and Y. Is that actually readable? I just realized I tend to write small. That's good. Okay. Right? And this is going to keep on going up to whatever the full adder for X and minus 1 up to Y and minus 1. And then I've got the resulting sum in minus 1. Should do capital because that's what I did here. Sum 1, sum 0. We've got our carry in slash. Now, how long in terms of the number of bits does it take to calculate this? Right? So why 2 bits?
Because we have to, well, we're going to add numbers to add. Is because we have X and Y.
So it's of these full numbers. Let's just put it in that way. That was better ways to get down to that speed. But all these yeah, it's because this little wire in between here for each one of these. Because the output of the first one goes into the second. That's the ripple here. And you have to get the correct value. This is what's going here. It's carrying the bit. If I did, it just regular stuff, 99 plus 1, you can't do those digits because otherwise you get 90, you know, you, you got to carry the digit over. And so you have to calculate each one as a bit. Therefore, you have to calculate each bit in sequence. It forces sequential operation. And this is what you're noticing is we have to learn that it's sequential. And even in electrical either sequential, but the way they're good, you have to wait until the sequential updates. Right? That's where that pops in. Right? It's got get intermediate answer. But that intermediate answer will be two period of time as sequential time is finished all the updates and stuff. Otherwise, it's just not bad. So, this is the complexity wise, it takes time, right? And full adders, right? Whatever a full adder takes. How long does this full adder take? Right? It's classical because is there anything here can be classical?
Not in speed, always because this is
We're going to read it into something. Right? But the hard is not being as forced. So we want to get down to a timing that's going to make sense in our hard way. Right? So what we're going to enter things in general gates. And the reason is gates can make it. So if we count the number of gates, if you make a better, faster logic family, then you can take in 10 faster gates. I remember we talked about it, you got pre-charge, evaluate, count. And as you switch to logic families, we can get faster gates. That will speed up. Right? So if you want to reevaluate this as gates, to do that, we're going to break up. How is a full adder built? This is the challenge, right? So this is going to become my full adder. So it's got an X coming in. I'm not going to worry about the bits, Y. It's got a C coming in. It's got an S coming out. And it's got a C out. Maybe I'll put a CI for C in. Right? How is this one? X, Y, and F, CI. Right? Should I?
So,
So you're correct, but the question is why? Okay? So I agree, we should do those together, but it's not for the reason most people are going to think of it first. We just think X and Y are similar put together. But who cares, right? It's not, so that would be a good reason. But why do X and Y separate?
it should be and
Yeah, they all kind of need, this is okay, it's better to do it. Since this is immediate, I think I can and it doesn't slow you down. All of them will do that happen in parallel because you get all the bits in parallel. You want to put the least amount of hardware between C and C. That tends to be as small as because if that becomes large, right, now you've got to have slowdown. So if I put C in the first half, two half. If I put C in the second half, very faster. So the best way to do this is actually to have, there'll be an extension of this too. We're going to have this little half adder in here. It's going to give me a sum and a carry. This is an internal, all right? So I'm going to put sum internal. And then I can take that sum bit and the carry and put it into another. And its sum bit goes all the way out. And then I've got these two carries, right? Carry two, carry one. And then I can either exclusive or these, whatever makes you happy, to get your output. Does that make sense? This is your standard. There's a picture of this. So you don't have to sweat this too much. This is a very good job. Zoom in on my small print. It's going to defeat my purpose of. Uh, yeah, my handwriting was legible. Right? But part of this one is really just so you can look at this, right? If I put that matter, if I had put CI into this one here in place of, for instance, I then you have to go through this one and its output into this one. Each of these numbers, if you remember, there's two gates to each other. So it takes one gate, and since I'm worried about my propagation is from here to here, CI to C out, the thing that slows you down. Okay? So I end up with 1, 2 days between this. That's the best you can do. If you look at CI here, you get 3. So 50%. Yeah. So, so I, I'm not avoiding the term clock here because there's no clock at this moment, right? The people come from X and reading something, but what happened internal? Nothing in here uses the clock. This is pure combination logic, so it has no notional sense of time. Right? There's no clocking involved to it. Where sacred it's just going to go. Right? So this is what we call register transfer. There's a register here that all that's it's on. There's a register that we call F, it's on. But in between, it's all combinational. And combinational has no sense of time. Right? So we've got a mixture, and if you the clock is slow in delivery. Think of that as right. It's, you know, it's, in one sense, you're thinking that, sort of the negative thinking is quick and quick. But compared to logic, which can be in people's it also knows we're magnitude faster than thought. It's a little because we need to be able to do a whole bunch of things between each things. So we need to think of this in terms of fastest law, which is what is your game? That is we use faster gates. And hopefully in the future, why keep pushing those gates? Because combinational logic push, there's an advantage there. So why go on to like doing single atom transistors? Because it's really small, really low power, and it should be blinding fast. Right? If we want to increase speed, there's got to be an upper limit. There's going to be lower size. At least in the moment on how we understand physics, we can't really help do this smaller than that. Right? It gets pretty challenging at the atom level, but there's going to have to do this with columns. So, it's at the end of the day, you know, in 3 years, the so, it's let's down even smaller. It's great. It's great. But this is where whatever limits we have at this moment, we want to take advantage of that. And that's where we take approach. Right? So that means if we look at this 2 gates, so I'm going to list all my things in terms of this. My timing takes 2. Now, usually speaking, so this is linear. So this is where we're going to put it. So this 2n is linear in n, the number of bits. So it's linear in its complexity, which we will often write as big O of n. Right? Anybody know what big O means? Complexity term? Big O's, there's little O's, there's omegas, there's all that stuff. What's big O minus? Yeah, I saw a hand gesture. What's the hand gesture for? In this case. Yeah, it's an up down the neck, in which case that we're going up here. And it's engineers. There's just that case in there, or something beat it on a best case, so it's that size. Omega, that's the one that tightly. So those are all considerations. Some of our engineering designs, first kind of care is what's the worst. As an engineer, in general, you're always thinking about the worst thing. Because if you make the worst thing okay, That's a good design. I, there are going to be a few cases where you will call a best case, because you might put alternatives. Like if I wanted to make it really, really bad, I'm not worried that every possible scenario, but use those scenarios to make it stupidly. I mean, and that's why people start using side panels, remove any speed. You start throwing out any unnecessary, because now we're in the worst case that you're in. So, right? You just blindly worry about speed. There is a place for that as an engineer, but that's not your general space. In general, you live in what's the worst thing that can happen, and make sure that doesn't get bad. That's why it's often described engineers are always thinking about the worst thing. Yeah. I mean, because if you don't, the worst case will. So in our case, this is it. Time-wise, we're big up, and that tells me an upper bound in worst case. And we're going to listen. So this isn't complexity. And we said slow. So I'm too slow for times. What's the big there? This is in terms of man, where's man in that big open? I said big one. It's not good. It's telling you it's well, can you do that for addition? Can I get a big 50 minutes? I can do it in
Is it possible based on being able to fix that one picture?
well, yeah, but one bit is right. You can't talk about complexity of one bit. It's gotta be. Let's just say in theory, is it possible to achieve bigger? Yeah, it is. Can you give me a proof? I can give you a really simple. Proof. Is it, you want to pay first? Okay, for a second. Okay. Why I can show very easily that it's possible in theory to achieve
To achieve a complexity of one bit.
bigger. That's the point is bigger. Explain all.
And how we're heading this way.
There's no sense. I would, I would,
Oh, I guess I see that. That's the comprehension.
have an end that is big on one. Yes, no, so yes, but I can show trivia that it is possible to achieve a big in you say
In theory, I guess, it's just like what your goal is.
well, simple. I can't describe you all working, but I have to be able to convince you that I'm going to at least draw a picture that shows the circuit that should achieve that. The problem will be that it's going to be hard to build. Right? And the problem will be correct. But you don't have to necessarily agree with why it is. I can draw a picture, absolutely draw you a picture, and I can give you a solid reason proof that when I say it, um, and it will be so stupid obvious.
Okay, so it's like,
We can do that.
it doesn't. It's like,
Okay, so that, uh, tell me what canonical form is. Like, Right? Um, can be described in canonical form.
Yeah.
If you can be described in canonical, how many watch is required in canonical form? Either SOP or POS. Right? Okay. At this point, I've got through it. There's this a because if you can draw through, I can write a canonical form, and I can reduce it to two levels. So you can, and you can always be expressed in two levels of logic. This I can do everything in two levels of logic, and they the input is constant, therefore you don't put the number there, so it's just big. Here's you just screwed. No, with this is that that's becoming time complexity. This is why this phase complexity. And this is why the same current issues. You're going to get binary in scale. Every one of the slides can be theory if it's right or not, it can edit all of the current, which means the current is going to grow proportional to the lines, and the lines are going to grow proportional to the number of bits. And then when your current is growing bigger and bigger, the size of your base is growing bigger and bigger. So the time space trade, this is the basic idea of it. Right? So I've got a field here. I can go, you know, you don't care. But unfortunately, so it's, and yeah, this is why in theory there's no okay, this is where we start getting, like we just hear about this time complexity is the horrible, right? This is one of the millennium problems, you know, can you do any problem, you know, in polynomial time on the machine? And I would say we know you can do much more than that. Can the deterministic machine do in polynomial machines? That's technically what the millennium problem complexity is.
All this like things that will work down.
Well, it's so algorithms become trivial. The reason why cryptography is safe and therefore cryptocurrencies and all the data stuff, a lot of these problems, the reason why it's safe is we don't know an algorithm that isn't like exponential time that solves the problem, right? It's wildly non-polynomial, right? It's the only methods we know. There are some heuristics, but they have problems. Right? So there's a huge number of problems in this area. We also know a non-deterministic Turing machine can solve any of these polynomials. Right? So by a non-deterministic, the simplest example of a non-deterministic machine is a guess and check machine. Right? And it's not just any guess, you have to guess the correct answer. Then you can verify what's the correct answer. Right? And you know, but I mean, in theory, this is something like machine. There's a couple there. Ones of these old people make a message on time. This is the right answer. And then how we know this is the right answer, then it becomes a question. Right? And people have asked me through the ages, right? Here's a question. Says X, Y, Z, and the end of the right? So then it's, I'm not very good at the should believe that. Just say, it's been a question humanity has through the ages. Ways to validate at least for these is for, you know, what's the two numbers or whatever I can give on 100 numbers, and you might not be able to get quite you can. But if somebody just did it, blah, 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 I mean, we have ways to check things fairly. It's because it's easier to check to build the solution. So a lot of our ones like, if I get what your password was, I could decrypt things pretty easily, and I could then verify whether something is or not, right? So if my guess was that the password or the private key or whatever your particular method is such and such, I could tell in very quickly whether that's correct. Does that make sense? So that's what we mean by an non-deterministic machine. And some people say, hey, that it's just a quantum superposition. Say, could we cause to just pull things hat? Right? There's a lot of different hats to get. I mean, I'm not concerned with doing this at the moment because we have to actually do this. And you know, there's no concepts that can do that. Without any questions. And if you want to talk afterwards, yeah, can be polls, and machines. There's even one in the real it's true multi-dimension, there's infinite numbers of you, and you guess that it will be if there's right? You know, that only the universe is where you exist to answer. But it has its infinite number. Never do this. We used to not be implemented. Right? These are junk machines, but the junk machines with a purpose. Right? Trying to get you to think what type of things could you do in different universes, different physics rules. Right? Because they don't necessarily have to have a person do that. I could just have a machine. We can like communicate across the dimension. Now, whichever one gets the right answer, has it. So now it's become a parallel machine. Right? When I need multi-dimensional parallel machines, you know, can I do that same thing with quantum superposition? And so we think of weird ideas of what might work, and we try to change them. So people come up with silly examples that do it, right? To be able to get these. But as yet, nobody can communicate across dimensions. We can't even put those dimensions on paper. They just seem like a reasonable business. So that's what I say. They're fun to think about. But yeah. So
This is it's like you guys would pass it back to the
yes. So that how do you get a machine like a jet time machine? I wasn't going to go too far on this, but I do want you to think about these. This is like one of the great mastery questions of ideas, right? And this is on a lot of the how you when we're talking even about how to do logic design, it turns out logic design is one of the NP. So if we want to do good logic design, right, we go to things like espresso, later, which are heuristics, right, rather than a fixed algorithm like Krusty. Because Brian Krusty can take two to the n to actually this videos to that logic function. And it gets crazy, you know. I mean, at 64 bits, right? You know, if you're doing addition, you've got 2 times 64, two numbers, 64 bits, all money. If you know, whatever, 120 bits. 129 is a ridiculously huge number. You're talking age of universe bit. It's bigger than age of universe bit. But that's there. It's something you have to be alive to see the answer. It's not how fast your machine will design is. Unless you have trivials. It's just it's the answer. So we would love to be able to beat this. So this is one where, so yeah, the thing about um, we have a machine that you never need to voice generate machine. It's called the answer register. And all you have to do is give me a time machine. So I make a register the whole data. And when you have a problem, you enter the algorithm in, and you check the answer register. And if the answer register has the answer in it, you're done. Right? And if it doesn't, you need the burden to do it, whatever time period it takes to do it, and send it to the machine to when you choose first. Then the answer will be there and you won't need to. right? Now, it's clean, even if you have a throwing machine, that's okay. Now, some people use this as a very time machines on phones because it's finding basic physics, right? So the internet and machines, but if you do it, these. People have tried the same idea, having a wormhole and send it away from you, and having a machine, and the wormhole brings the answer back immediately, right? And maybe a time dilation between the two, so I get a machine, I can do the analysis and it sends it back, and I can do a wormhole version. How? Okay? So that gives specifics to it, but you can't go holes, they have information connections and stuff. But maybe you don't need to apply for it, you just got to figure out how to do that. And that's awesome if you do, right? But that's why we think about these things. They sound stupid, but today time research can become advanced. It really is. It's fiction, but you're trying to share the ideas of what we're talking about. People who don't think wrong never. That's all you have to do. Absolutely, science fiction great stuff. I love it, right? So I just mentioned this because engineers, we want to be practical, we do. But we do want a little bit of impractical theory because that's the next generation of solutions. And so that's we live between these two realms, particularly as you go. With this, I and the proof that I could get a debate along is just canonical forms. I told you once to show this, it's pretty easy. Right now, it doesn't look in the mechanics, but in an update, it's to do is write them in instructions. That's what we're going to actually do. We're going to do this, not going to get with a small. It turns out it's fairly straightforward to show that you can get a good expression for four levels of function, four gates, to be able to do this. Right? Maybe three. But anyway, this slightly larger one is very easy, and we have built this one. Now, the one is this, as they built it, and again, the more inputs you have, the worse it gets. Right? So it's you have to stop. So what we actually do is build what's called a block carry overhead. A problem is those carries. So what if I took this and instead I bring all these wires and I built a machine that's going to calculate this and calculate the carries into those. Right? Or roughly speaking, that means simple, right? Cycles. Yeah, because now they're going to be worried about this form coming out. And you're going to do it next generations. That's a 30. Leave it there. I just have two levels. And then the carry in coming in from the level. We'll do these in blocks. We'll show you how. It turns out it won't quite achieve what we want to react. If you did the full design, and we'll show you how you could do the full design, but then we'll show you just our method to try to build it. Because too much current. That's always the problem. Going to come down to the current on this one. That's what we call the spatial complexity. So we're going to dig into this and see why. The idea and the goal makes sense. Because we're about to do some ugly algebra. Right? And partway through ugly algebra, you're going to be like, what the heck am I doing this for? Remember, we're doing it because we want to find a very fast level. I'll show you how you can do it in two carry what we have. Carry what we have. you say space complexity, you just yeah, the complexity is well, the complexity is that since these are cascaded, the way the wires are pumped up, it will take time for them to finally operate. So in most cases, we're going to be dealing with the gate. On one of them, it's that the gate's cascade. The other is going to be parallel. So time complexity kind of looks like, here's gate one and here's gate two, right? And I have them going, this involves a time complexity, right? That there's two levels and da da da. I could have more going on, right? What we're going to talk about space complexity is what if I have a big gate and I add more and more wires to it, right? So it's going to require bigger gates, right? And those bigger gates, when you reach those gates, a single transistor and every wire carries current potentially into that junction. And you have to do so you're going to end up with 10 wires, and that's how we. So as it keeps growing, as n goes to 50, goes to 50, right? Which means tau after this state goes to infinity, right? And a finite thing cannot dissipate an infinite amount. So it will, right? That's what I mean. I just can't handle. Right? In practice, about 8 to 24 wires is about the biggest. Pretty much any logic family will take 8. CMOS, low current generator can do 8, 12, or 16. I've seen a couple families so they can handle the inputs. But I don't know maybe it was supposed to be on 20. Right? So that just becomes, it's visual imagine specialized. Right? So that's when we stop it and we have to go bigger gates like cascading gates together. Right? But the and the output of two AND gates together makes one big AND gate. But now I've got multiple AND gate levels to get through an AND gate. So again, we call it building this cascade. That is um, so this is a big idea that's coming in. I'm mostly out of room here. What else? Hopefully I can go the other way. This is just the way I'm used to writing. Let's consider the first bit for a sec, right? So I'm trying to calculate some bit 0, right? So we're going to assume the gates, right? I've got x0 plus y0 plus potentially c0 carry coming into it. Adding those three together gives me some 0, right? And it carry, well maybe yeah, some 0 carry to 1. That makes sense? All right. So I've got kind of, all right, this number appended is equal to the x0 plus y0 plus c0, so on and so forth for each bit that's later down the line. So we could say in general, this is just appending them together, right? So, carry 2 sum 1 is equal to x1 plus y1 plus carry 1. So on and so forth. But that plus is really addition. So in general, I could say ci plus 1 sum I is equal to xi plus yi plus ci. Do we agree that's a step of this? So I'm just keeping this in mind when I'm building them, right? That means I can write expressions for each of these. So let me start by writing the necessary expression for each of these. So what does it look like? How do I get sum 0? This is arithmetic, right? I want logic gates. So you can't just use uh, the fact that plus in arithmetic is addition and plus is or. So you gotta make sure you get the language.
This is where the solar and
Right? So we've got XOR to get our sum, right? Because XOR is odd. So I can go and say X0 XOR Y0 XOR C0. I believe I can do XOR. Right? This right here just looks like X0 Y0 C0. Boom, here is S0. Right? It's one gate. I don't have to do it in stage half. So I the other. But notice I have increased the number of stages to reduce the number of stages. It's trade between how deep the stages, which we consider proportional to the time it takes to solve. It's a time complexity versus the width of the inputs. Give me wide inputs so I can consider multiple things together. And I can do it in less time stages. That's time space trade. You will find this in every field you have to solve. This is going to be a major engineering time-based trade. Whenever you do any algorithm, when you build any, you can always trade off your space position. Even thinking about transmitting on a bus, okay? You give me a wider bus, I can send in less time. Right? Increase my bandwidth and it decreases the time that it takes to send the signal. This is right, a basic idea. Space trading is all over. Sense? Okay, how about C0? Or sorry, C1. How do I figure out what gives a carry in this case?
carries
Is it just
no if it's
okay? Yeah, you're exactly correct. The problem is, in this case means 2 or 3. So how do I know whether it's 2 or 3? Oh, yeah. So here's one thing, right? If it's also, if, in order to be 3, you have to at least have 2. So, I'm going to check 3, I check to check all 2 possible. And as long as one of the 2 possibilities wins, then I don't have to worry about the 2.
so
So, pretty simple. But how many 2 possibilities? Well, could it be 0 and Y0? Is that a 2 possibility? What are the 2 possibilities are there? X, right? And C0. We also have Y and C0. And how do I combine one more?
because one through
We need one speech. Right? I need both to be true. That's why it's and. I can do or here because that. But notice that in order to again reduce this, I needed a 3 input or. Right? I had 2 input ands, right? X0, Y0. I had all these other ones that were, X0, C0, and I had Y0, C0. All right, there you go. That's C1. All right, so far so good. Okay. Now you can get this one, yeah, you just on one gate. Just two levels on here, depending on where you're at. So far, so good, right? Now, I could obviously reduce this to hands and overs if I wanted to. I'm not going to, but I could make it hands and overs. Because exclusive or there's just, yeah, it just, again, gets complicated over two levels. Let's take a look at just C2, and I think will be able to see how this works. How do I get just carry 2? All right. Well, one thing I could do is I could just take this and increment all of the variables. Oops, X1, right, and C1, C1. So I can increment the, and then I can say, well, the only thing I don't know here is this one, which came from the previous level, but I can take the expression for C1 and stick it in. All right. So that means the same C2 is, well, this doesn't need any substitution. But C1 here, I've got to grab this expression. X0, Y0, X0, C0, or 0, C0. Or, show up two of them, whatever, and it is same thing repeated. Three. Okay. That is an expression, but you'll notice it's not in two levels of logic. But imagine algebra, I can extend this. I'm not saying it's pretty, but I can do it. All right. So I can take, again, this first term doesn't need to change, but I can use distributive and distribute the x1 all the way through. Right? So I'll get x1, x0, y0. Do I have to? Right? This one going here, or it carries in here, x1, x0, c0, um, x0, x1, y0, c0. Actually, let me do x0. I'm going to redistribute mine just so they're all next to each other with my x's are next to the x's. It doesn't cause any problems here. It just puts them in a nicer order. 0, c0. Now, is this two levels of logic? How big are your gates? Gates and for gates. I, uh, when these parentheses are needed, right? Because they're not doing anything like separating orders, right? So I could run 1, 2, 3, 4, 5, 6, 7 of these into an OR gate. That's a 7 input OR gate. So 3 input AND gates, 7 input OR gates. Notice what I need before? I needed 3 input. right? 3 is 1 bit less than 4. 7 is 1 bit less than 8. If you're wondering how 3 is 7, see the manual pattern going on here. And same thing with 8. You know, think about what's going on. On the first one, I had 3 different possible inputs, right? And now to generate them, I've got those 3 plus another 3, so I've got 6 of them. So it's kind of going proportional to the number of available bits, right? There's 3 inputs in the first one. There's 6. The 3 first ones plus the 3 second ones on the next, right? How many possible bits do I have coming in if I want 3 bit numbers? 3 bits for caps, 3 bits for pi, and 10 be, you know, it's getting ugly, isn't it? Right? Right? Typically speaking, if you look at it, right, I've got number of inputs. If we make a little chart here, uh, inputs. I've got 3 inputs on for our first size one, and we had a 3 input OR gate. Right? This is just size. For when we had the next level up, 1, 2, 3, 4, 5, 6, 6 inputs. And how big was it? 7, right? 3 inputs here. This one took 7 inputs, right? If I do the next one, I'm going to take this, I'm going to increment all the numbers, right? And in essence, I'm going to be replacing for this will become a C1, 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 and I'm going to substitute the C0 back in. Right? So each one of those is going to generate 3, right? Every time I do it, I'm getting those additions based on this. We want to, I think we do this one, maybe 2 more, uh, that if you want to look at them. It's just like this one, it's like we actually, it's a huge, machine do that, to look at the food generating. Right? Generate us billions of bits. I didn't really want to do, just make the machine go expansion. If you look at each one of them when they're coming in, right, I've got at the next level, when I increment these, this will become x2, I2. That'll be one term. Right, then I'll have x2, um, x1, y1, right? So that'll be a second term. And then I'll get these x2, x1, and then I have to substitute in the expansion, right? And then I'll have x2, y1, and then substitute in the expansion. And each of the expansions can triple. So I'll have 1, 2, I'll get 3 from here, I'll get 3 from here. This one will give me a third. I'll get 3 from here and 3 from here. That makes sense? So I've got 3 plus 3 times 4. Right? 3 times 4 is 12 plus 3, 15. So I get 9 goes to 15. All right. What would happen, right? If you think on that next level, you can see, right? I had uh, originally 2, it went to 4 of these. But we're going to have 8, right? And that'll have to get substituted in. 8 times 3 small. So it's yeah, each time you go up a level, we're getting right 8 times the 3 from here plus, well, this one will be 8 on it, right? Um, you know, because you'll get all of these. or I should say 7. Sorry. 1, 2, 3, 4, 5, 6, 7. There'll be one constant from each one. And so I'll get 7 on those. So the next level I'll get 7 plus 8 times 3. That's what's going to go here. Right? 8 times 3 is 24 plus 7, 31. And how many inputs did I have? 12. Right? Do you see the pattern going on? Right on this side, um, if you just have this was a 1-bit number, 2-bit number, 3-bit, 4-bit. So my inputs, right, as I'm growing, right, I've got all these carries too, which I'm counting on, which makes it a little bit more complicated, right? And you could say, hey, maybe there's something I can combine. Um, um, Sadly, it's not going to be really an easy one to do. So just for the moment, we just consider this 3n, and this is looking like 2 to the n minus 1. It's it's growing pretty nicely. Yeah, there's so pretty. Yes, there's then I could right. The problem is actually space complexity. Yes, because I think it's like one for one. But building things bigger and bigger, there's just limits to what I can handle before things break. Right? Even if you want to get a mechanical terms of power, how many level companies friction of companies becomes so great? So you get a machine, it's an electrical machine, with current, you do anything we can think of to build. You can build a space where you can rebuild on something. Right? And it's you have a finite. Right? If you consider how big the universe is, I mean, it seems pretty huge to us, but if you the whole universe full of electrons, you could only get somewhere into the 500 electrons. Pretty big damn number, right? I mean, that's, but, you know, that's assuming roughly 39 billion light years, standard time. So it's just, it's huge, but be that huge of a number to take, at least we can describe if you want to get that out. That's atrocious, right? But that's more than the other things in the universe. But now you get communication delays between these things, actual data. I mean, there's just the universe can't handle spatial lines. Right? So the spatial lines almost always worse. This is why there's limits like every limits on space. That's a space line. Right? So spatial complexity is worse than time complexity, and time complexity is lower. Just to give you an idea, limits, really big fundamental limits people don't get all of it. Do we feel good? Or do we at least feel we understand this? Right? Now, this being said, I cannot do something. I could do this, but so we say, except we can get something easier. And this is when we step back and we say, okay, let's just try to get a machine that can generate my carry bit that's coming out. And if you notice, we have a lot of terms. If you look here, I've got a bunch that look like x times x in series, right? And y1 times y0. We get a bunch of these type of terms. And as a matter of fact, we get a lot that at the same level, right? We get, the x1, y1. We get the x0 times y0, wherever I stuck that. Um, here, right? You get a bunch of these cross terms that come in, right? Now, think of what that means in terms of a carry. If at the same level, I knew that x bit and y bit were both 1, what do you know about the carry that exists, right? Because you have 2 ones at the same level coming in. It's 2 ones at that level. So you've got 2. So if you've got one, we call that generate. it will generate a carry. This is the trick to simplify this.
So errors and some line and say, hey, we're the one. So great.
Yes. So we know that on this generate, right? That's the 2 bits, right? This is xi and yi, right? Now notice that I can do for especially the first half of this, right? We added those 2 bits to generate the carry, right? And the exclusive order to generate the sum. We're just using that carry function. We can give it a new name, generate. It's guaranteed that that has the third one. We know if it's true, there's you will get it. So we call it generate. We can know it in parallel, right? I can also know, and this is going to look like cheating, but I'll show you why it'll fix in a second. We're gonna, since that generates, the other thing that could happen is a carry can propagate, right? So propagate is going to look like either one of those are set. Now notice that's just the sum in essence out of this, right? Or close to it, right? It's technically speaking, I could also take an exclusive or in here, right? But it doesn't matter. All it is, as long as one of them's in, so I'm just going to do or, right? If x and y, either one of them is there. So we're going to do or. These are two we're going to call or. It actually technically x or y. Because I do want, if they're both, I still want to say something's happening. Although I will say this, the reason why I say it doesn't matter is because if you put xi exclusive or yi, right, the propagate will be wrong in the case of um, if they're both on and there was a carry, but if they're both on, it generated. Of course, it doesn't matter because technically generate will take that case for me. But if you want to be very technical on this, this is what's defined as propagate with an or, because it means if there's ever a carry below it, that carry will generate. And I'm seeing an over case, there's a case for both. And so they both, if I wanted to save space, I could replace it with an XOR and just take half adder and generate take over. So that's why it's true and true all at the same time. I, but as long as you understand that trade, in reality, we all will just take that XOR and generate a take over. But in the expansion, it's no, we're going to run a whole bunch of these in I, and we're going to, what you need in the landscape is we will need the carry from the previous level. But I'm going to show you we can expand one instance. And we can figure it out, at least in block form, we can expand it. And what we'll say is if propagate and carry, okay, um, that or generate, we will generate a carry to the next level. Yeah. Which one is the CI? Right, so this is CI plus one. Right, my bad. Right, so CI plus one is generate from I, right, or propagate from I and right. All this is saying is is no video. Either there was a carry coming in and I can propagate, or a new one just started at this level because the bits were right. We agree? This is fair? Okay. Now, what if I took this and did my recursion trick and expanded it? Because this is a legitimate expression, right? So I could say, well, CI has to be equal to generate from I minus 1 or propagate from I minus 1 and with C from I minus 1. And I can use these two together to say C from I plus 1 is equal to generate from I or propagate from I, and CI was this. Generate I minus 1, propagate I minus 1, CI minus 1. Expand, generate from I or propagate I, generate from I minus 1, or propagate from I minus 1, and C I minus 1. Do we agree? And notice that all these ones, both propagate and generate, are one level of logic from the end. Now, this is the thing. I just know the things. I'm not going to say that's the first half. I literally build the first half of all the best. Right? And I'll use the inputs, right? I'm going to use the sum as my propagate bit. And I'm going to use the carry as my generate bit. But the moment carry, right, there's no save there. When I can understand this gets me back to carry time minus 1. But I could then pick in and expand this too, could right? I could say, well, what if I wanted to go back another level? What if I wanted to go back not to I minus 1, but to I minus 2? I just have generate I, propagate I, generate I minus 1, propagate I minus 1, and then again substitute in an expression. This is for I minus 1, so it'd be generate for I minus 2, or propagate for I minus 2, right? And carry for I minus 2. Agree? And you'll rapidly see there's a pattern to build all these bits. Generate I, propagate I, generate I, minus 1. Propagate I minus 1 times generate I minus 2, or propagate I minus 1, propagate I minus 2, ended with C at I minus 2. Theoretically, please and. All right, see how that's going? Yeah, it's pretty exciting. This is actually linear. So this is pretty nice as far as I go. I think this is big. It's just achieving current in here. Then with these, but I'm still going to hit a limit. What I have to do is board to generate propagate and generate. Build them. Does that make sense? Carry log ahead. Because each one of these G is on the command. You're supposed to be able to stack or, right? So this just requires the inputs, one data. Again, it's just input. There's no previous thing. And again, it just requires the half numbers data. And that's the same thing here. If you look at I minus 1, I minus 1, I minus 2, I minus 1, I minus 2, and then you turn it. But no, so that I'm not like being the generator. I mean, this is too little. The amps get, but there's like two levels here. It just has to go to one path, because you still have the original and it's what gave you something. I mean, you don't need to carry, they're being generated. So you can just forget the carries. You just have to get the first half out of the gate. Okay? And you work together with what you get, right, from the carry in from the previous level. That's what you're ordering. So, those four, one half matter, two levels to generate the carry, and one level to buy it back in. Four levels. And if you build this as big as you want, and you have this linear switch company, you know, to generate with linear space complexity. Linear space complexity, right? And I'll show you very quick. But this is pretty essentially the expression is give you you build this. Yeah, this is what we're going to do next time. A lot and talk about how we go blocks and how we just figure out go figure out what it is. So so all the anytime about our we have it's always full. Full. I'm excluding that half. Okay, then it's always full. It's always two levels here. I need a number for you know the this is one, two, three, four. So it's going into that. And move on to the organ gets paid. This don't make it just a single line. This is a two-bit gate, a three-input gate, a four-input gate. So the AND gate is bringing four inputs to the AND gate, four inputs to the OR gate. Add another level, you have one more turn. So you get five to five. Linearly with the upper data. No, that's growing. It's growing at space. This is two. It's always two. And eight into OR gates. Yeah. Look at it, maybe, right? You know, just keep like as many as you want to couple. Pretty soon see you can expand it so it's always two. Good. Don't forget that there's an talk, just right after this. My own master's student, Marcia, is defending, so please make sure